Okay, so we're recording now, and so this is the second supplementary session, and unfortunately I won't be able to annotate today because the iPad's not working, so we'll just try our best with the computer. So these are the learning objectives that we already went over, so I'm just going to skip over these in the interest of time. We briefly talked about how we could have, you can see my mouse, right?
Yes.
Okay, good.
Yes.
So we talked about how we could have a 1D signal in discrete time here, and or else we have continuous time signals, and the main thing from last time was we said that we could represent any signal. In this case, it's a 1D signal as a sum of delta functions, like so. Okay. So today we're going to change a little bit, and we are going to say we want to represent signals as a sum of sinusoids. So for example, if we wanted to represent this signal here, we could use a lot of delta functions, or else we could say that this signal here is the sum of these three signals, each with a different frequency and each with a different amplitude. And so, for example, the Fourier transform then would be saying, I have a signal at this frequency with some amplitude, another signal here with some amplitude, and another this with some other amplitude. Excuse me. So that's the basic idea behind the Fourier transform. And what we want to do today is sort of get a much better sense of, provide you a much better sense of what the Fourier transform is and how to use it. So this is the definition of the Fourier transform. It has a deceptively simple form where if I have some function g of t, in this case, g is a function of t, where let's say that's time, I simply take that function, I multiply it by e to the minus j 2 pi ft. So this is what's called a complex exponential. And then I just integrate that over from minus infinity to infinity. And we denote this as big G of little f, where f here represents frequency. So we can write that g of f is the Fourier transform of g of t. We can also use this notation where we're taking the Fourier transform of g of t. And the amazing thing is, once I have g of f, I can take g of f and I can multiply it by the complex conjugate of this term. So the complex conjugate of e to the minus j 2 by ft is simply e to the j 2 by ft. So the only difference is here there's a minus sign, and here there's no minus sign here. Okay, and this equals this if under the right circumstances, it equals g of t. So this is now the inverse Fourier transform, and we denote that as f inverse of g of f. So I want to talk a little bit about units. The two things we'll be dealing with this class is we'll typically be dealing with functions that are a function of time. So when we talk about MRI, we'll talk about different types of waveforms that are a function of time. And so in that case, we typically use t, and that will be in seconds or milliseconds or some sort of form of time. And then in that case, f, the frequency will be in cycles per second or hertz. Okay. And then the spatial coordinates here are, we will be talking about things as a function of space. And so, for example, when we look at images, if it's a 1D image, then it would just be a function g of x. And in that case, x would typically be in centimeters or millimeters. And the kx now, we use k sub x to denote spatial frequency. So we could have kx for the x direction, ky for the y direction, and kz for the z direction. And this is typically in cycles per centimeters. Okay, so it's sort of useful to sort of have a sense of what those units are. In class, Professor McVeigh reviewed a little bit about Euler's formula. And so in this case, just to remind you, e to the j theta, this complex exponential, is equal to cosine theta plus j sine theta. And an important thing that will be especially important once we get to MR is to really get sort of comfortable with this e to the j theta notation and realize that this theta if I represent the real and imaginary parts, as we do typically for complex numbers, then the theta is just the angle between this complex vector and the x-axis, okay? So e to the j theta has the magnitude of 1, okay, because cosine squared theta plus sine squared theta equals 1. And then it has an angle of theta, all right? So hopefully this is somewhat familiar to most of you from probably trigonometry in high school. So that means what we can do is write out the Fourier transform. So we can take this complex exponential and expand it out as a cosine and a minus j sine term. And so when we do a Fourier transform, we're saying, how much does g of x look like a cosine? And how much does g of x also look like a sine? Okay. And then basically the idea is g of kx is how much this function g of x looks like a cosine with this particular frequency or a sine with this particular frequency. And the reason we need cosine and sine is because you can have a cosine of, if you just had cosine, but the cosine is at one place in space, and you need to be able to have a cosine with any phase shift to it to represent your signal. And so if you remember the cosine sum formula, if you have cosine A plus B, then that's going to give you cosine A times cosine B minus sine A times sine B. And so any cosine that's shifted with a phase is going to split into cosine and sine terms. And that's sort of one way to think about why you need both cosine and sine for the Fourier transform. Now, so far we've talked about 2D Fourier transforms, which typically we'll start off with, we start off with 1D Fourier transforms, and it's typically easier to start off in 1D. But for this class, obviously, we really want to do 2D Fourier transforms. And these are a little less familiar to people, but the definition is actually fairly straightforward. We basically, instead of a single integral, now we have two integral signs. And now instead of a function of one variable, we have a function of two variables, g of x, y. And now we have a complex phasor that instead of just kx plus kx times x, we also add a ky y term. And now we have to integrate over dx and dy. And similarly, we can have the Fourier transform. So we can have little g of xy is equal to the sort of the inverse Fourier transform of g kx ky. So now you can sort of see we have both a spatial frequency in x and a spatial frequency in y. And in this case, to get the inverse Fourier transform, we're integrating over dkx and dky. And note that the book uses u and v instead of kx and ky. I'm not really sure why they do that, because when you look at academic papers in MRI and CT, it's much more common to find kx and ky. And so that will be the notation we'll use for most of this course. Okay. But just as you're reading through the book, you'll just have to note that they use u and v instead. Okay, so let's take a little look at this, what this means. So if I have e to the j 2 pi kxx plus kyy, then I can split this into cosine 2 pi kxx plus kyy plus j sine 2 pi kxx plus kyy. Okay, so let's look at the case where, let's say, ky equals 0. So we can ignore this term here. Then we're just going to end up with cosine 2 pi kxx. Okay. Now, this is still a two-dimensional function, but it only depends on x. So if this is the x-axis here, it's just basically, it's the same value for all values of y, okay? But it varies along the x direction with this cosine. And so if you imagine these lines representing the peaks of the cosine, where the cosine is equal to 1, this is how we would represent this, okay? And the period is just 1 over kx. Okay, because when x equals 1 over kx, then you get this goes back to 2 pi. So that's one cycle. So you can sort of note, so anytime you see cosine 2 pi kxx by itself, you want to think about a one-dimensional, a sort of two-dimensional function that varies only along the x direction and there's no variation along the y direction. So in this case, this would be at some value of kx. We're not sure what value that is. And in this case, ky would be equal to 0. Okay. Similarly, we can look at cosine 2 pi ky y. In this case, the kx, we're assuming the kx is equal to 0. And so there's no variation along the x-axis. All the variation is along the y-axis. And the spacing, the period of these oscillations is 1 over ky. Okay. And now if you have the case where you have both kxx and kyy, then it turns out you're going to have variation both along the x direction and in the y direction. And the spacing is given by this formula, 1 over square root of kx squared plus ky squared. Okay, so it's just the Pythagorean relationship. Okay, so any questions up to now? Okay. The next slide is just showing, how you could sort of, if you had two lines with spacing 1 over kx and 1 over ky, from basic geometry, you can derive that this spacing here is 1 over this expression. Okay. And the other useful thing to note is that this theta is equal to the arctangent of ky and kx. If my pencil was working, I would sort of draw this out more, but we'll try to pick this up again at a later time. Okay, so the first part I want to do today is really just give you some intuition into what's going on with these spatial frequencies. So this is from the book. Once again, they're using U and V for kx and ky. But let's look at this first row here. So all of these v's are equal to 0, right? So that means there's no variation in the ky in the y dimension, okay? All the variation is along the x dimension. So in this case, we go from 1 to 2 to 4. And you notice as we increase that spatial frequency, the spacing between the peaks gets shorter, because remember the spacing is 1 over kx. So kx of 4 is going to have a spacing that's 4 times as small as when kx is equal to 1. Now, if we look here, the only thing that's changed is, well, there's a couple of things that have changed. Now we're keeping this first term equal to 4 the whole time, right? So this is kx equals 4, kx equals 4, kx equals 4. And so if you notice, the variation along the x direction from this peak to this peak, for example, from here to here, that distance is the same as this distance, is the same as this distance, okay? So along the x direction, the distance between the peaks is the same, okay? Now what we've done here in ky is it's going from 1 to 2 to 4. And so let's look at this. From here, along the y direction, from here to here, let's say that's 1 period there, right? And that takes up the whole square. Here, I only have to go half the way across the square to get 1 period. And here I only have to go a quarter of the way across the square to get 1 period. Okay, so what's happening here is the horizontal frequency is staying the same, but I'm changing the vertical spatial frequency. And so that's giving me different diagonals. All right, so these are the basic building blocks of the Fourier transform. And the claim is going to be any image, we can build any image with a collection of these types of building blocks. So typically we talk about the term K-space is used quite a bit in medical imaging. And what that means is if I have an image space, an image like this, which is a function of x and y, then in K-space, I would have the function as a function of kx and ky. And you notice this looks very different, right? So this is my image, and this is Fourier transform. So we want to spend some time trying to understand what different parts of the Fourier transform, how they correspond to this image, okay? And we'll find out that in MR, the image is acquired in this domain. And so the MR machine actually acquires the data in this domain. And then you can take the data and simply pull it into MATLAB or any other program, do the inverse Fourier transform, and get your image, okay? So let's look at little different parts of K-space. So here is the kx axis, and this is the ky axis here. So if I'm at this point in kx, So here's a point for some value of kx, and at this point, ky is equal to 0. Ky equals 0 means that there's no variation in the y direction. And so this would represent some sort of image component that only varies in the x direction. Okay. Now, as I move out farther in k space, we still have ky equals 0, so there's no variation in the y direction. But you notice that the spacing between these peaks is now twice as small as between these peaks, because I've moved out twice as far out in k space. Okay. Similarly, if I go along the ky axis, here kx equals 0, so there's no variation in this direction. There's only variation in the y direction. And if I move out farther in k space, that corresponds to a component that has twice the spatial frequency as this component here. And if I move out diagonally here in k space, then I'm going to have variations in both x and y. Okay, so every point in k space is going to correspond to some pattern like this. Okay. And so the idea is we can take any image and decompose it into these patterns. So this represents sort of the building blocks that I'm going to add up. So as I go along, each row here is what I'm adding. The second row here represents the cumulative sum. So this one represents the sum of these two. This one represents the sum of the first three. This one represents the sum of these four. And and as you can see, as I add these building block components, I'm slowly building up my image. Okay, until at the end I have this image here. All right, and so that's the basic idea behind Fourier transforms, is any image can be thought of the sum of these sort of patterns of variations along x and y. Okay, so hopefully this movie will play. So what you're going to see in this movie is we're going to start off by just having information from the center part of k space. And you notice it's a rather blurry image because all these values here correspond to images that have very low spatial frequencies. So the variations are very low frequency. And then as I add more and more of k space, you can see we're sort of filling in the details. Okay, and so by this point, we've done a pretty good job, and you can see all the details. So that's one of the basic intuitions you want to have about this Fourier transform, is that the center part of k space here is really the low resolution. It's the overall shape of your image, okay? And then as I get more and more outer parts of k space, I'm gradually filling in the finer details, because these points in k space correspond to spatial frequencies with higher spatial frequencies or finer details. Okay. So that's the basic intuition you should have. So let's do some examples before I have you guys do an exercise together. And then today we'll try maybe splitting people into a few breakout rooms so you can discuss this. So let's look at this. So basically we have, this is my image and this is Fourier transform, okay? And what I've done here is I've just zeroed out these parts of the Fourier transform, okay? And so all I have left is this, okay? So remember, these parts corresponded to variations going in the left-right direction, and I've gotten rid of all of them. So let's see what the effect on the image is. This part of the brain here is called the corpus callosum. It's sort of like a superhighway connecting the two parts of your brain. And you notice here, if I go along this direction, these edges now are a little more blurry, okay, going this way. Whereas this edge, if I cross this edge here, which is the edge I see if I walk along this direction, this edge here is still fairly sharp. Okay. So this means I've lost the information that I need to represent edges that I would meet as, so the edges, sort of these up-down edges, these vertical edges are blurred out, or I've lost that information. Similarly, if I zero out these parts of k space, I've lost information about edges that are sort of going this way. Okay, so if you notice here, this edge here is now blurred out, where this vertical edge here is fairly sharp. Okay, and if I take out all the edges, then you can sort of see that I'm losing detail in both this direction and this direction. In fact, all these directions. I can play a similar game where I can just zero out the parts and only keep the information about these edges. So remember, these are the edges. These correspond to vertical edges. And you can sort of see here the image now only really has vertical edges. It's lost these horizontal edges. Okay. If I keep the information on the horizontal edges, then it preserves that information, but I'm losing the information about these vertical edges. And if I keep all the edge information, then I'm just basically ending up with an edge detected version of my image. And then I can also think about if I just add some energy out here in K-space. So I've just added a point here in K-space. So remember this is along the KY axis. So it's going to add edges. It's going to add horizontal edges to my image. So you sort of see that here. Okay. If I go off here along both KY and KX and KY, that's going to correspond to horizontal diagonal edges. Okay. And so that's shown here. The rule of thumb is if you think about drawing a line from the center of K-space, so this is the center of K-space out to where you are in K-space, and draw perpendiculars to that line. Okay, so in this case, the line goes from here to here. The perpendiculars to that line represents what the edges look like in image space. So for example, here I go from here to here. That's the line. I draw the perpendiculars to it. That represents these components. Okay, so what I'd like to do now is we're going to, let's see, how many people do we have? So we have 8 of you. So what I'm going to do is I'm going to split into, just randomly, we're going to split you into 4 breakout sessions. Okay. And here's the job. You're going to, so A corresponds to this. So this is just the Fourier transform. So now you want to match B, C, and D to either 1, 2, or 3. Okay, so that's the job. And so I'm going to put you into breakout rooms for a couple of minutes. You can discuss this. Since it's a small group, we're not going to use the polling. We're just going to ask people what they think. Okay, so any questions before I send you into a breakout room? Everyone understand what to do? Okay. Yeah. Let me give that a try. So we're going to create 4 breakout rooms. And we're going to create that. And okay. So go ahead and discuss that in your breakout rooms. Okay, so I think we're just waiting for 1, 2, 3, 4, 5, 6. Okay, looks like everyone's back. Okay, great. So go ahead and either through the chat or through the mic. First question I'm going to ask is, and I realized I could use this annotate feature, so that's good. Is which of these images, B, C, or D, has the most information? So if you were to look at B, C, and D, which has the most detail to it? D, right? Yeah.
D.
So, yeah, D definitely has the most information, right? Did I just do that? Oh, did someone else draw that? Okay. And then, so then which of these Fourier transforms, 1, 2, or 3, has the most information?
1.
1. Yeah, so I would connect this one and this one, right? Can everyone see the annotations that I'm drawing?
Yes.
Yes.
Great. Okay, good. So I can use that for the rest of the lecture. Okay, so now that's the easy part. Now let's think about B. So B it clearly has these edges, right? Edges like that, right?
Mm-hmm.
And so would that correspond to 2 or 3? So we can either
2.
2, right? So this would correspond with 2, because remember these parts in K space, right? If along the K y-axis, that corresponds to these sorts of components, right?
Mm-hmm.
Okay, and therefore by process of elimination, C would go with 3, because you notice we have these vertical edges here, right?
Yes.
And then if I go along the K x-axis, then we said that it's these components like that, right?
Yeah.
Okay, so that's the basic understanding. So if everyone's okay with that, we're going to go to the next one. We'll just keep you in the same breakout rooms, since you already sort of probably met your partner. And so let me just say, oh, okay, geez. So I guess the annotation stays on for all the other slides.
On the bar that pops up during annotation, there's
Yeah.
like a clear space, like clear
Like
the
this?
annotations option.
Clear all drawings?
Yeah.
Okay, great, thank you. Okay, so this is your next test. So we'll give you a couple of minutes to do this one. So 1, 2, and 3, A, B, and C. Okay, I'm going to open the rooms now.
Also, when you send us to the rooms, it doesn't keep the projected image.
Oh, okay. So it's in the if you go to Canvas, it's in the PowerPoint.
Okay.
Okay. Okay, looks like everyone's back. So let's play the same game here. So which of these images has the least amount of information now?
A.
A, right? So definitely A. Annotate. So yeah, A has the least amount of information. So which Fourier transform would it correspond to?
3,
Which-
3.
3, right? Because 3 has the least amount of information, right? So that's good. And then let's look at B. So B clearly has these vertical edges, right? So which one would it correspond to, 1 or 2?
1.
Yeah, 1. Because remember, if we go along the kx axis, then that's these vertical components. And this one clearly has these sort of lines like that, and that would correspond to, we go out in k space.
Yes.
All right. So that's that one. Any questions on that before we move on?
Yeah. So what exactly are you referring to when you say like vertical edges? Here, let me annotate. Because here I see that there appears to be almost like some like streaking artifacts out here that are horizontal. So I would tend to think that that would be like horizontal edges because of those streaks.
Yeah, that's a great question. The idea is that there's probably some weird artifacts that we'd have to sort of spend some time explaining. So what we're talking about more is if you look at the most dominant features of the image, right? Like where there's a lot of signal, that's what I'm looking. I'm looking at these edges here.
Okay.
Okay, and then here I'm looking at these edges here, right? When it's in the noise level, it's a little hard to, out here, it's a little hard to say what it is, but definitely these edges, right? The vertical,
Right.
vertical edges are here, whereas you notice the top of the brain is sort of gone, right?
Oh,
Or there
and then
should-
like maybe this region here where like the horizontal region is completely missing.
Exactly.
I
Yeah.
see.
Yeah. So
Yeah.
that's missing where it's here. It is here, right?
Yeah.
Right.
Yeah. Okay. So that's a great question. All right. Anything else? Okay. Let me clear this. And we're going to move you to the last one. So everyone, so I guess make sure you have the Canvas things here. Now there's 4. There's 1, 2, 3, 4, A, B, C, D. We'll give you a few more minutes to do this. It was a little slightly tougher problem, but I think you guys are up to it. All right. So sending you to breakout rooms now. Okay, looks like everyone's back. So let's take a look at these images here. So these are rather complicated looking images. They all have a brain, and then they have different stripes. So they, which of these images 1, 2, and 3 seems to have the least complicated interference to it? Like where there's only stripes in one dimension.
1.
1.
Yeah, yeah. So 1 only has stripes going up and down, right? Okay. So which of A, B, C, and D would 1 correspond to?
A. Maybe A.
Okay, so let's look at A. If I draw a line out from here to there, right? And I drew perpendiculars to that. Oops. That would tell me sort of the pattern. So given that, which one do you think 1 would correspond to if we use that rule?
Oh.
B.
B?
B, right? It would go with B, right? Oops. Happened to my annotation. It would go with B. Okay. Because remember, if I did this, then this would have lines like this, right? Okay, sorry. Sometimes the mouse doesn't quite pick up as quickly as I'd like it to. Okay, so that's good. So then so 1 has these vertical stripes, right? Which of these other ones sort of also has some vertical stripes to it?
Three.
Yeah, 3's got vertical. So if you had to guess, so which of A, B, C, or D looks similar to B, right? Which of these, B's got a line this way, right?
Mm-hmm.
So which of A, C, and D sort of has a similar looking line like that in K-space?
C.
C, yeah. So this would most likely go with this, right? And let's think about this. If I draw a line from here to here, and I draw the perpendiculars to that, it does give me these lines, right? I can sort of see those stripes there, right? And then these patterns here, the vertical patterns, the vertical stripes, right, are sort of left over from the fact that I sort of have this extended range of frequencies out here, okay? And then similarly, if we look at this has got these vertical stripes. So it's going to correspond with this one, or the diagonal stripes are in that direction, and then this one would go this way because it's got stripes like that. All right, so that's basically just sort of a really sort of just giving you guys a sense of what K-space looks like and how different components of K-space correspond to the image. Okay, any questions before we move on? Okay, I'm going to clear this annotations and we're going to move on. Okay, so now we're going to transition into computing transforms. And so we're just going to go through some of the most common ones. We're not going to go through all types of Fourier transforms. The easiest one is the Fourier transform of the delta function. And that is given by this expression here. And remember from the sifting property, the delta function, if I integrate the delta function with any function, it simply picks out the value of my function at x equals 0. So I put in 0 here, this becomes e to the 0. So that's just picks out the value 1. Okay. Similarly, if I have a shifted delta function, delta of x minus x naught, that just picks out the value of this function when x equals x0. So I just put in x0 for this, and so that gives me e to the minus j 2 pi kx x0 or x naught. All right. And then the other very common Fourier transform you'll be seeing a lot is the Fourier transform of the rect function. So remember, the rect function is defined from -1/2 to 1/2, and it's the transform of this. And you can all do this integral because it's just an integral of an exponential, which you all know how to do. So it's just, e to the x, transform of e to the x, or any e to the u is just, e to that u divided by the du dx. Okay, so If we plug that in, we get this expression here, and we can simplify it into sine of pi kx over pi kx. And we define this. This is so important that we give it a name, and it's called the sinc function. Oops. Hold on. Let's get the annotation. So we define this as the sinc function. And what it looks like is, let's see, we get some axes here. Be a little bit more straight. Oh well, it's close enough. It sort of looks like this. And it goes on, you know, obviously to plus or minus infinity. Is a value of 1 at 0, and it crosses the 0 at integer values of 1, 2, 3. So at all the integer values, it crosses 0. Okay. So we're going to see a lot of this function. You've already seen a little bit of it in some of the CT lectures. You'll see a lot more of it in MR later on. Okay. Okay. Next one is, what is the Fourier transform of 1? Okay. So let's plug that in. So the 1 is just here. So there's no, 1 times e to the minus j2 pi kx is just itself. So once again, we can sort of try to think about evaluating this. But the problem is we're going to have terms like e to the minus j2 pi kx times infinity, right? Because when we evaluate the exponential at infinity. So here's a question. What is e to the minus j infinity? What is that equal to? Any ideas?
I think it's 0.
Okay, so one possibility is it's 0. Okay. Any other thoughts on what it could be equal to?
Wouldn't it be negative infinity?
Okay, the other thing is it's negative infinity. Okay. Any other thoughts? So if it's 0, then probably this is going to end up be 0. So Fourier transform 1 would be equal 0, which would be sort of weird. Or else if there's a negative infinity, then it's going to have, Fourier transform of 1, which is a nice number, is going to be minus infinity or something, which would also be a bit problematic. So remember when we talked about complex exponential, it's like this vector where theta, this is theta, right? So anything that has e to the j theta is just this, right? So it's just saying that this e to the minus j theta is just this vector with a phase of minus infinity. But that's not really well defined, right? We don't really know where on the circle it is because infinity isn't a defined number. So unfortunately, this is not really actually defined. So we don't know what that equals. Okay. So it turns out that we have to to get the answer, it's a little more complicated than we can go through, but we have to do what's called generalized functions. And it turns out that for this course, all you need to remember is the Fourier transform of 1 is equal to the delta function. Okay, so that's sort of our first Fourier transform pair, where we found out that the delta function, Fourier transform of that, was equal to 1. Okay, and now we just found out that 1, Fourier transform of that, is the delta function. All right, so that's good to keep in mind, and that's a nice, the first Fourier transform pair that we're going to have. Let me clear these annotations. Okay, the next thing we're going to talk about is using that we can also have a Fourier transform of a complex exponential, and that's just a shifted Dirac delta function. And this is really important to remember because it means that anytime you see something that's e to the j 2 pi k naught x, you can just remember that this is something that has a frequency of k sub naught, right? And that just means that the way we represent that in Fourier space, so along the kx axis, this would just be a Dirac delta function located at k sub naught. So that's nice, because that sort of makes sense. It means if I have something that has a spatial frequency of k naught, then in the Fourier domain, it just has this one component that's located at k sub naught. Okay. Now let's look at the Fourier component of cosine. So remember, cosine can be written as e to the j 2 pi k naught xx plus e to the minus j 2 pi k naught xx over 2. So I can split this into two Fourier transform, one at kx minus k naught and one at kx plus k naught. And so this would have, its Fourier transform would look like this. We'd have one component at k naught, okay, and the other component would be at minus k naught, and they both have area of 1/2. Yeah, and similarly, you can do the same thing for sine as you do for cosine. So this is a question that I think someone asked Professor McVeigh, and he asked me to address this, is that here you have what's a positive frequency, and here you have a negative frequency. So the question is, why does cosine have both positive and negative frequencies in its Fourier transform? So let's take a look at that. So if we look at this here, this is a complex exponential with a positive frequency. And so you notice it's a phasor that rotates this way. Okay, so if I draw that phasor, it's rotating like this. Okay, so because it's getting positive phases as a function of x, so it's e to the j theta, where theta is becoming more positive, so it's going like this. A negative frequency is shown here. This is kx equals minus 0.1, and so you notice this is rotating the other way. Okay, so as a function of, as x, so this is the x-axis. As x is increasing, it's getting negative phases, whereas in this case, when x is increasing, it's getting positive phases. Okay, it turns out when you take these two phases that are going in opposite directions, and you add the two together, then you just get something that's a cosine. Okay, because everything on the imaginary axis, this is the real axis, it's the imaginary axis, everything along the imaginary axis cancels out. So because when this is going up, this is going down. So at every point in space, those imaginary axes cancel out, and you're just left with a real part, which is the cosine. All right, so here's the MATLAB code for that. I've also posted on Canvas. You can play around with that if you'd like. That's one way to remember why the cosine has both positive frequency, which goes this way, and negative frequency, which goes this way. When we get to MR, we're going to see that this has real physical meaning. And so that's very interesting that we're actually going to, in MR, these phasors are actually going to correspond to the spins, the orientation of the spins in space. And so these are actual real implementation of the phasors in actual space. Okay.
Wait, really quickly, for clarification, when you said this one and then that one, and we're moving your cursor, can you clarify again which one is which? The negative and the...
Yeah, so this one here is the positive frequency, right? Kx equals 0.1. And this one is the negative frequency, kx equals minus 0.1.
Awesome, thank you.
Yeah, and then if you're really interested, you can always go through this code. And this is the exact code that was used to generate these figures. And it's posted on Canvas. Okay, so moving right along. So what we've just sort of seen is sort of a form of duality, which is, if I have the Fourier transform of a complex exponential, it goes to a delta function or shifted delta function. If I have a shifted delta function, it goes to a complex exponential. So this is a form of duality, which is very useful. It means if you know the Fourier transform going one way, then you typically know the Fourier, you can sort of guess at what the Fourier transform is. Mathematically, it's given by this expression, okay? But let's just do an example of it that's useful. So here's the question. What is the Fourier transform of sinc of x? So I could take minus infinity to infinity, integral of sine pi x over pi x, e to the minus j 2 pi kxx dx, right? So it is possible to evaluate this integral, but it would probably take most of us quite a lot of time to do that. We'd have to sort of remember all the different ways of integrating, you know, maybe separation of variables, you know, different tricks. In any case, it would take quite a while, okay? But from duality, we know that the Fourier transform of the rect function is the sinc function. So duality says, okay, then what I can do is that since I know, I can just take the Fourier transform of sinc of x. Since I know the Fourier transform of rect of x with sinc of x, I know that the Fourier transform of sinc of x is just rect of x with a minus kx in it. Okay, that's how I apply that formula. And then since rect of x is symmetric, rect of minus kx is just equal to rect of kx. Okay, that's nice. So basically we have that a rect goes to a sinc and a sinc goes to a rect. Right, and so that's another thing that is very useful for you to keep in mind, that the rect, oops, that's not what I want to do. Let's erase that. If I have a rect function, its Fourier transform and the inverse transform is the sinc function. So it goes both ways. If I have a rect, it goes to a sinc. If I have a sinc, it goes to a rect. Okay, so that's probably one of the more useful pairs to remember for this course. Okay, the other property that we is useful to know is the separability function property. And this just means that sometimes you can write a function g of xy, which is a two-dimensional function, as a product of two 1D functions. So in this case, a function of x and a function of y. And the separability just means if I know the Fourier transform of each of these, and this is the case, then the Fourier transform of the product is just the product of these two Fourier transforms. Okay. Now, big warning. Do not confuse this with the convolution theorem that hopefully we'll get to later today. Okay. The important thing here is that these two have different variables. This depends on kx, and this depends on ky. And because of that, we can just multiply them together. The most important example of that for this class is if I have rect of x times rect of y, which is a two-dimensional sinc function. So it looks like a two-dimensional rect function. That's this function here. Then there's a separable function. So I can write it as the Fourier transform of this one, which is just sinc, and then the Fourier transform of this one, which is sinc. So one is sinc of kx and one is sinc of ky. Right? And that's shown here, where this is my two-dimensional rect function, and this is the two-dimensional sinc function. Okay, so we'll see a lot of this in throughout the class, where we're going to have a lot of these rect functions because we're going to be sort of delimiting what area we look at. And then anytime we do that, we can imagine in the other domain, it's going to be involved a two-dimensional sinc function that looks like that. Okay, I'm going to leave this for, the question is the function separable and was its Fourier transform? I'm going to leave this because we're sort of running behind on time. Just going to go through a few simple examples. The two-dimensional delta function is separable. So this goes to 1 and this goes to 1, so the product is 1. this is sort of a tricky one. The two-dimensional function delta x equals delta of x, but we have to remember that's actually means delta x times, times 1, right? So this goes to 1, but this goes to delta of ky. So that's, since it's a two-dimensional function, it's a delta function in x. And so what it would look like if we were to draw it would be as a function of x and y, it's like this blade. It's a blade like that. So it's only non-zero when x is equal to 0, but it has all the same values for all values of y. Okay. The other important thing to know is the center of k-space. And so that is basically, if I take g of 0, then this term goes to 1. And so it's just the integral of my function, either in 1D or 2D. And so that's basically anytime you have a function, the center of k-space is always the area under the curve. And this is proportional to the mean value of the function. So the overall, if you have a lot, it's sort of the mean sort of, value of the function. And so anytime the center of k-space tends to be the brightest spot in most biological examples, because that's just representing how much of the sample is there. All right. Other things are the Fourier transform is linear. So that means if I have two things and add them together and multiply by constants, I can just get the Fourier transform like that, just by taking the Fourier transforms of the individual functions, multiplying them and adding them together. This is an example here where I can take 1 plus e to the minus j 2 pi x, and I take the Fourier transform of this, which is a delta function, and I take the Fourier transform of this, which is two delta functions. Okay, and so this is just applying linearity. Probably the more important one is the scaling theorem, and this is one where if I have rect of x here, it goes to sinc of kx. Okay. Now, if I take rect of 3x, that's a squished version of rect of x. Okay. And according to the scaling theorem, that should go to sinc of kx over 3 divided by 3. So this has an area, this has a height of 1/3, and its first 0 is at 3, where this had its first 0 at 1. And this is really important to remember. It means anytime you have a function, you squish it in one domain. So in this case, I've squished it going from here to here. I've made this narrower going from rect of x to rect of 3x. It means I dilate it in other domains. So I squish in one domain and I dilate in the other domain. And that'll be really important when we're looking at sort of application of this to imaging. So these are the Fourier transform pairs. And these are just sort of useful to know, and some useful facts and definitions. There's also a version of that in the book. So the last thing I want to go over is just to give you a sense, because of time, we're going to just have to give you sort of the meaning of this. We're not going to go into great detail on how to derive it. But the idea is that we can represent things either as impulse responses. So here, it's called LSF, which is line spread function. So these are sort of functions that are the impulse responses. So you can see as I go in this dimension, this response is getting broader. Okay. And if I take the Fourier transform of these impulse response, that's what's known as the modulation transfer function. And so that you can sort of see that as I'm broadening in this domain, I'm getting narrower in this domain. So that's an example of the scaling theorem at work here. Right. So let me just ask everyone a question. These are basically three different systems, right? Okay. Would you mind, someone's not muted. Ksenia, could you mute yourself? Some background noise there. Okay. So of these three systems, which one of these do you think is the best system? Which one would be the most expensive system to buy? So you can either enter through chat or you can just say it.
The first system.
The first system, yeah. The first system would be the most expensive system because it has the narrowest impulse response and the broadest frequency response. So those two things tend to be require much more engineering to get something that's this narrow in one domain or this broad in the frequency domain. So what we want to talk about is, we've talked about last time about if I have a system with an impulse response of g of x, and I put in an input, sort of h of x, and I put in an input g of x, my output is just the convolution of g of x and h of x, right? That's the whole thing with convolution. So the really important thing, and probably one of the more important things of today, is if I convolve two things in one domain, I actually get the product in the other domain, okay? Now the important thing here is this is not the separability theorem, because notice here that these two things are both a function of kx, okay? And so, whereas before we had kx and ky, when we multiply things that have the same, depend on the same variable, then in the other domain, it becomes convolution. Okay, whereas with separability, it just stayed as a multiplication. So that's an important thing to remember. That's a very common mistake people make. So, and this goes both ways. So for example, here, if I multiply in the image domain, I convolve in the frequency domain. Okay. Let me just walk you through why this sort of makes sense, and then we'll look at some examples. Just clear the drawings. Okay, so remember, this is some signal that I'm splitting up into different Fourier components, right? And I can represent its Fourier transform as the amplitude of these components. And now imagine I'm going to take this whole signal and put it through some system with an impulse response, h of t. And that impulse response has some frequency domain response, h of f, okay? So I know from last time that the output y of t is just g of t convolved with h of t, okay? But I can also look and say, well, this system has this frequency response, so it's going to modify each of these components by the value determined by where it is in frequency, okay? So for example, you notice this high frequency gets attenuated much more going from here to here than this low frequency is not attenuated very much, okay? And so the output is also just the sum of these components, right? Because I could break this into these components, multiply each of them by the appropriate value, and then sum them up afterwards. And so I know that the Fourier transform of my output is also just taking this g of f, multiplying by these things, and then the output is just g of f times h of f. Okay, so that's sort of the intuition behind the convolution theorem. I'm going to skip over this. This is just showing that it's because of, these are eigenvalues of the system. Oh, sorry. Yeah, we'll skip over that just because for time, but this is just, it comes out because complex exponentials are eigenvalues of convolution. So let's look at a nice application of this. So here we have the rectangle function that goes from -1 to 1, okay? And the question is, what is the Fourier transform of this function? Now, you could obviously evaluate this by hand using probably separation of variables, okay? But it's much better if you remember that this function is what we derived last time, is the convolution of a rect function with a rect function. And so that means that this function here is this convolved with this. Therefore, we know its Fourier transform is the Fourier transform of this one times the Fourier transform of this one. So that would just give me the Fourier transform of the triangle function is just sinc squared kx. Okay, so that's a way where we can use this convolution theorem to help us do things very quickly. Obviously, you can do it in 2D as well, and this is what we'll show in a few minutes, where if I convolve in one domain in 2D, it's just multiplication in the other domain. And similarly, if I multiply in one domain, it's just convolution in the other domain. So here's an example here that's going to be very important for MRI. So remember in MRI, what we'll find out is we collect the information in the Fourier domain, as shown here. Okay. And this happens to be the Fourier transform of this object, the rect function. So here I have a rect function going to a sinc function. Now, I may not have the time or the money to collect all this data. So what I might want to do is I only want to collect data in a little region of Fourier space. Okay. That's equivalent to taking this function and multiplying it by this rect function here. Okay. So if I take this function and multiply by this function, I get this function. So the rect function here is useful for delimiting, how much of Fourier space I collect. So I've multiplied in this domain, so therefore I must convolve in this domain. So let's look at what happens. This is my original function, g of xy. I'm going to convolve it with the Fourier transform of this. Now this is a rect, so this is just a sinc. And you notice this sinc is much broader than this sinc function, okay? Because this got squished. This is much narrower than this rect function. So therefore this sinc function has got to be broader than this function. So I'm going to take this rect function and convolve it with this sinc function. So every place I have something, I'm going to replace my dot with this function. And if I do that, I get a blurred version of my original object. All right, so this is how we apply these concepts to imaging, that as we collect less data in one domain, it's going to lead to these sort of artifacts or blurring in the other domain. Another thing that's useful to know is that typical in most systems, you'll have many modules. And if you connect them together, you can get the output as the convolution of all those modules. And since this is convolution, it means you can get the frequency response as being the frequency response of all those frequency responses multiplied by each other. Okay, so what that means is if I had 3 modules, A, B, and C in my system, then multiplying all those together gives me my frequency response. Okay, so let me just ask a question. So I have 3 modules here, A, B, and C. Let's say they each cost the same amount to replace. They each cost $1,000 to replace. Which one of these should you replace to have the most improvement in your system? Should it be A, B, or C?
A.
Yeah, you want to replace A because A is really the limiting factor, right? A is the narrowest. So if I could make A a little broader, like out here, then that would have the most effect on the system. Okay. So for example, so that's something to keep in mind if you're ever having to make system choices. And lastly, the modulation. So the last thing we'll end with today is here. It's a form of the convolution theorem where now I'm taking some function and multiplying it by another function. And in this case, I'm multiplying it by a complex exponential. And that means I take my Fourier transform and I convolve it with a shifted Dirac delta function, because the Fourier transform of this is a shifted Dirac delta function. And so this just gives me, remember, anytime we convolve a function with a shifted Dirac delta function, we end up with a shifted version of that function. Same thing with taking something g of x with a cosine. It's going to just shift it with a delta in one way at k naught, and also delta at minus k naught. Okay. So the example of this is used every day in it's called amplitude modulation. There's actually many types of modulation. For example, your cell phones all use a type of modulation, and it's essentially taking one function and multiplying it by another function. So in AM radio, you multiply it with a cosine. On your cell phones, if you're using like, well, most cell phones today, use something called CDMA. It's multiplied by like a random set of signals. Okay. But there are all types of modulation, and so the way we can understand that is if I take my function g of t and multiply it by cosine, then I get g of t times that cosine. What that does is, if this is the Fourier transform of g of t here, and it's located around the center of my Fourier transform, my axis, this just takes this and shifts it here and here, okay? And it turns out for a broadcast reason, you want to sort of move something like an audio frequency up to a higher frequency. So audio frequencies tend to be around in the kilohertz range, like 5 kilohertz, whereas AM radio is in the 100 kilohertz range. And that's because you want to get the wavelength of the electromagnetic wave small enough that you can broadcast it efficiently with reasonably sized equipment. And then finally, the imaging example of this is here. So let's say we have an object here, and its Fourier transform is a rect function. This is a rect function, and it says Fourier transform is a sinc function. Okay. Now, if I multiply this by this stripy pattern here, okay, then I'm just going to get this image here. Okay, it's just a square with stripes in it. Now, this has a Fourier transform. You can't really see it here, but it should have 2 little dots here where the direct delta functions are. And so it means I'm going to take this one and I'm going to shift it one way and shift it the other way to both positive and negative frequencies. And that would be the Fourier transform of this function here. Okay. And then finally, there's the shift theorem, which if I take any function and shift it, I end up with the original function multiplied by some phase term. So the magnitude is not changed, but I end up with this additional phase term. Okay. So these are the basic properties. And what today was just really sort of giving you an overview. What we'll do is, especially when we cover MR, whenever we use one of these properties, we'll review it. And then so you'll have a chance to see it again. And we'll sort of remind you of these properties as we apply them as we're doing MRI. But it's helpful to see them at least once beforehand because then you have something to refer to. Okay. There's also a table in the book. And that's all I have for today. So we got a little past time because of the technical difficulties, but if there's any questions that people want to ask or hang around to ask questions, I'm happy to stay for a little bit. Okay.
On a few slides earlier, can you clarify again why you would want to replace A? And then also maybe what would happen if you like chose some of the other ones to replace?
Sure. So let's say, so this system response here, so you have A, B, and C as the system responses. And then what we've said is that if you have 3 things in a row, then the output response in the frequency domain is just the multiplication of A, B, and C, right? So imagine if I took A, if I sort of replaced A and made it something that was, let's say, very flat like this, right? Almost perfect response, right? So I got rid of this, right? Then imagine just multiplying B and C together, then I'd probably end up with a response like this, right? So it would widen my response out because I've gotten rid of the effects of A. So now my response can be wider. And typically a wider response is better in the frequency domain.
Okay, thank you.
Sure. Any other questions?
I was going to ask about like the Fourier transform.
Sure.
So when you do a Fourier transform, you typically get a complex value, right? Like part of it is a real value, and then part of it's usually imaginary.
Yes.
And then you take that and you basically do a calculation to find the magnitude, and that gives you the amplitude of the frequency of whatever wave you're trying to find. And then you do another calculation to find the phase, right? The arctan. Arctan. And then my question is like, so when you like plot the like wave, let's say you want to know like for us, like let's say, I don't know, like 50 hertz sine wave, or I don't know, yeah, sine wave, like when you find like at that, like at 50 hertz, this is what my magnitude is, and this is what my phase angle is. Like, how would you plot that on like a graph? Like, how would you know, like, how do you determine where that wave is on a graph, if that makes sense? And how would you plot it?
Well,
if that makes sense. Yeah.
Sure. Let me just see if I can. I'll answer something and then I'll see if it answers your question. And if not, please feel to follow up. But so you're correct. Every the Fourier transform is a complex transform, and so in general you'll have real and imaginary parts, and so that can also be represented as magnitude and phase. So typically, you would have two plots. You'd have a magnitude versus frequency plot, and then you'd have a phase versus frequency plot. So you'd represent the magnitude and phase as two different plots. Is that your question, or is your question how do you represent that complex exponential?
My question is like, once, let's say you want to draw the sine wave that you just found, at that amplitude, how would you draw it based on the calculation you just made? Like, you know the amplitude and you know the phase. How would you know, how do you determine how much it's shifted to the right from the origin?
Right. Sure. Okay. So basically, so let's just say, that's a good question. So it gets back to understanding, this complex exponential e to the j theta, right? Right. So any number we get, any Fourier transform we get, we can have some magnitude a, let's say, and it's going to be a e to the j theta, right? Okay, so every complex number we can write as a e to the j theta. And we know that e to j theta, the theta is just simply the angle, this angle here, theta, right? Okay, so theta equals 0, if you imagine theta equals 0, then that would just be like the cosine, if I have something like e, for example, to the j, let's say 2 pi f t, right? Plus theta, right? Okay. So then you can sort of say, okay, for whatever frequency I have at t equals 0, right? The angle is theta, right? So so you basically, you would know that, for example, if theta was equal to 0, right, then I would just have my, I can just have my cosine function, right? Assuming that this was just all real, right? So this theta just sort of tells me what my offset is.
I see. So basically, if your theta is equal to 0, it's all just a cosine wave. But if theta is not 0, then it's a combination of sine and cosine wave? Or?
Yes, let me see if I can make that more clear. Let's see. So we have e to the j theta. Yeah, I mean, let me sort of try to write that out, and I'll send something out about that, because I think it's going to be too complicated. Without my pencil, it's going to be very hard for me to do it here. But yeah, let me write something out and send it out. Okay.
Okay. Thank you so much.
Sure. Okay. Any other questions before we sign off? Okay, so I think that was obviously a lot of material, and just to sort of ease your mind that this is more just making sure you get exposed to the material, and then we will, as needed, review it as we do MRI. But it's good to just have seen it at least once before, and you can always refer back to this video if you need to. And then if there's more questions, or people feel like they would like more supplementary sessions, or for example, there's things like sampling and things, just send me an email. There might be a need for maybe one more session, but I'm going to base that on sort of, people sort of demand, because I know everyone's very busy, and I don't want to sort of, make people feel like they have to come to another session. But if there is enough demand, then I'm happy to help. And otherwise, you can always ask questions by email as you have questions come up. Okay, so I think what we'll do now is we'll end the recording and have a good weekend.